Hi everyone. This is another attempt at the plane question. So we've got a plane experiencing thrust and drag. This term represents thrust, the T term, and the C V squared term represents drag. I messed this up quite badly in a tutorial, so I'm making this video to fix that explanation. This is a separable nonlinear equation. We've got a v squared, so it's definitely nonlinear. It's amenable to partial fractions, so let's separate. Let's also anticipate the partial fractions and factorize this t business. Factorizes nicely. And we can integrate. We've got to do this with partial fractions. So that's where we write where a and b are constants to be determined. So we'll clear the denominators. And now this equation must be true for all v, so it must be true for each particular v. So let's choose some convenient values of v that simplify this equation. Right. We choose the roots of these factors, right? So one of them will go to 0. In this case, the b one goes to 0. Zero, 2t. Simplifying, we get a equals 1 on 2t. The other one, or the b, can be determined with v equal minus t on c. We substitute that into our expression up here. This one goes to 0. This one goes to 2t again. So this implies that b equals 1 on 2t. So when I, oops, there should be a minus sign there. It's minus there. When I did this question originally in the tute, I did what I nearly did there and missed that minus sign. And I got that b was equal to minus what it should have been, or a, I can't remember. I messed up the sign on one of them. Now that we have this, we can take it and plug it back into this expression to obtain the separate partial fractioned integral. The integral we can actually do now that we have this, we can integrate and simplify. These integrations technically have to be done by substitution. So if you want to check that out, this is the substitution you use. I'm just going to be really careful. And take the shortcut. So we get a C from there when we integrate, and we get a minus sign as well. And we've got some constant of integration C0. Now we can rearrange, and when we do our rearrangement, I'm going to do something a little bit odd, but hopefully it'll become clear why I do that later. I'm going to move the 2C around, 2TC, and I'm going to use our rules to collapse the logarithm into a single log. Okay, so we get this expression. Now we can exponentiate, rearrange the constant, and get rid of the absolute values. This is plus or minus e to the c1. All right. At this point, I'm going to muck around with this constant. I'm actually going to put it back up into the exponential. Right? So a is equal to e to the log of a. Let's put that back in. Now, log of a is a constant. That means that's also a constant, right? It's just pulling out convenient factors. Now I'm going to call this whole piece of junk, I'm going to call that K. So what I've obtained is T plus CV divided by T minus CV equals e to the 2TC T plus K. All right, now I've got to rearrange this expression to find my variable of interest of V. Right, now we can rearrange. We put this C over here, and we put this T over here to match with the T terms. We've just got to keep track of all our factors. CV, we're going to get a plus on this side. So we're going to get 1 plus E, the 2TC T plus K. Then on this side, we're going to get equals T into e to the 2TC T little t plus K minus 1 from that factor there as it goes over this side. All right. We're now going to divide it. I'm going to write it in a slightly different order. e to the 2 t c t plus little t plus little k minus 1 over e to the 2 t c t plus k plus 1. All right, you can go and check this definition online. This is equal to sine over cosh, our hyperbolic functions. This thing we call tanh. Tanh of x is equal to e to the 2x minus 1 on e to the 2x plus 1. Okay, so I've even got this factor 2 in there. So I can write this as t on c tanh reordering very slightly so that I can directly compare with the solution from Wolfram Alpha. And we've got it right, finally.